We're going to talk about OpenMP and hybrid programming. So this is our second half today. So here's our outline. So first, we're going to talk about OpenMP and what it is. We're going to learn some OpenMP directives. We're going to learn about data scope, which is a really important concept in OpenMP. We're going to learn a few runtime library routines and environment variables. And we're going to learn how to use OpenMP, and we're going to have our little interlude, and then we'll do hybrid programming, and we'll have an interlude there too, where we'll combine everything we learned into one thing. Okay, so let's go. So let's learn about OpenMP. So OpenMP is the industry standard shared memory programming model. So it was originally developed in 1997. The OpenMP Architecture Review Board, ARB, determines additions and updates to the standard. In fact, a member of my group is on the OpenMP ARB. The current standard is 5.0, just came out in November 2018. So probably most compilers by now have at least some part of the 5.0 standard implemented in them, but maybe not all of it. I'm not actually sure about the status there. So here are things that I like about OpenMP, especially compared with MPI. So one thing you can do with OpenMP is you can parallelize a small part of an application, and you just start with a small part and then work your way through. Whereas with MPI, you really have to kind of completely restructure your code from the get-go. And so you can just begin with like, oh, here's a part that takes a really long time. It'd be super nice if that could be parallel. And you parallelize that, and then your code runs, in a shorter amount of time. And then there's another part, and you say, oh, I'm going to parallelize that part. So it's just really great because you can just do that kind of iteratively. You can express very simple or very complex algorithms in OpenMP. I mean, you can in MPI as well, but OpenMP is just a lot more clear to see it. Because this next point, I believe, the code size grows very modestly with OpenMP. And so, we'll see some examples in a few minutes, and you'll understand what I mean here. It's really easy to read your code. You can clearly see where the parallelism comes in to your code. And you can use a single source code for OpenMP and non-OpenMP. If your compiler doesn't do OpenMP, or if you turn off OpenMP, the compiler will simply ignore those directives. So those are some really cool things about OpenMP. So the programming model is an API that is a combination of directives, and that's the majority of it, runtime library routines, there are a few, but not very many, and environment variables. And within this API, there are kind of three categories of things. So there's expression of parallelism or flow control, data sharing among threads, so sort of communication, and then synchronization, so coordination or interaction. So the parallelism is shared memory thread-based parallelism, and it's explicit. You have parallel regions within your code, and it uses what we call a fork and join model. So there's a thread running along, and then it forks into a bunch of threads within the parallel region. And then when the parallel region is done, then it joins back into a single thread. And then it does that again, if you have another parallel region. But that's kind of the structure of how it works. Okay, so let's talk about OpenMP directives. And of course, I had to have something about the prime directive. in here. Otherwise, I would have lost my nerd card. So that's why we have that picture. So we'll talk about the syntax of OpenMP within your code, and then we'll talk about the parallel directive, loop directives, sections, synchronization, and reduction. So here's your basic format. So if you're a C or C++ person, this is your format. So it's in the format of a pragma, and it's called, so pound pragma OMP, and then the name of the directive, and then any other parts of the clause, and then a new line. So all directives have to be followed by a new line. So that's just a carriage return, you don't enter. Pragma means thing done in Greek. The pragma is case sensitive, and it follows the standard rules for C or C++ compiler directives. So you use curly braces to denote the scope of a directive. So if it's coming along part of your code, a long piece, then you need to use curly braces, and they have to be not on that line with the pragma. The reason is because, like before I said, your compiler, if you turn off OpenMP or if it doesn't support OpenMP, it's just going to ignore these pragmas. And so it's also going to ignore that curly brace if you had it on that line. And then it's going to see the curly brace at the end, and it's going to be like, hey, what the heck? Where's the matching curly brace? So that's why it needs to be on a separate line. Long directive lines can be continued with an escaping new line character. So with a backslash, and then you hit enter. And then it'll know that it's a continuation line for the next line. All right, if you're a Fortran fan, then the format is you have a sentinel, and then the directive name, and then any kind of clause. There are 3 accepted sentinels, so that's exclamation $OMP, star $OMP, or C $OMP. And some directives, instead of having the curly braces like you would in C, you have like a beginning and an end. You have like an end directive clause. And so if you're a fixed form Fortran person, then you can use any of these 3 sentinels, and they have to begin in the first column of your code. The initial directive line has to have a space or a 0 in the 6th column. And a continuation directive line has something other than a space or a 0 in the 6th column. And then, of course, you have to follow all the standard rules for fixed form Fortran, like line length, spaces, things like that. Now, if you're doing free form Fortran, which is what I would encourage you to do if you're a Fortran user, then this exclamation point $OMP is the only accepted sentinel. It can be in any column, but it must be preceded by only white space and followed by a space, at least one space. If you're going to do a continuation line, you end the first line in an ampersand, and the following line begins with the sentinel. And then, of course, you have to follow whatever rules for freeform line length, spaces, things like that. Okay. So the first directive is parallel. So this is exactly like in the picture how it was the fork and the join, right? So it's a block of code that's executed by multiple threads. So here's our syntax. So if you are a C or C++ person, this is what it's going to look like. Pound pragma OMP parallel. And then these are kind of optional additions, private and shared, and we'll talk about those later when we talk about variable scope. And then you have your parallel section where you do your parallel things, whatever those things are. And if you're a Fortran person, here's your Fortran. And I just did this to illustrate to you what it would look like with a continuation. And yes, I mean, I guess this could technically be, no, it can't be a fixed form, but this is free form Fortran. But anyway, so you'd have your parallel section, and then like I said, you know, in C or C++, we use these curly braces. In Fortran, we have an end parallel sentinel at the end with the sentinel that signals that this is the end of the parallel region. Okay, so here's a simple example. This is a hello world sort of a program. Here's what happens. So we include our OMP.h. This is our header file for the OpenMP functions. And we have an integer variable that we define, and it's for the thread ID. And it says, you know, hello world from threads. And then we have our parallel section here. And like I said, we'll learn about what this means, but basically what this means is that every thread gets their own copy of this variable called TID. So TID is set to OMP get thread num. So that's the same as MPI com rank, except for OpenMP rather than MPI. So it's getting its rank, its thread number. And then it's going to print out its thread number. And then we're going to end our parallel section here. And we're going to print I am sequential now and return 0. Okay, if you're a Fortran person, this is the same code, but written in Fortran. Okay, so let's say we're going to execute it. So we execute it once. It says hello world from threads 0, 1, 2, 3, 4. I am sequential now. We're using 5 threads apparently. Okay, then we run it again. It says hello world from threads 1, 2, 0, 4, 3. I am sequential now. So the purpose of this is to illustrate that the order of execution is scheduled by the operating system. So these threads are parallel. So you should never try to count on threads executing in a particular order, because the operating system will schedule them. And 99.999% of the time, you would probably get this 0, 1, 2, 3, 4. But then there's that 0.001% of the time when you get a different order. So one issue that often happens with people when they're using OpenMP is that they implicitly depend on some type of ordering in the threads, and they don't quite realize that that's what they're doing. And if they do that, then they're going to run into trouble, but not every time, just sometimes. So the next one is called loop. It has 2 different forms. So the iterations of the loop following the directive are executed in parallel. So the syntax in C, it looks like this: pragma OMP4. And then there's these optional arguments. And we'll talk about what these mean. And then you put, you know, the curly braces around the actual for loop. So in here you would have, you know, for I equals 0, I less than n, I plus plus, you know, whatever it is that you're iterating over. In Fortran, for loops are called do loops. So it's OMP do, and then you can schedule, and then your loop goes in here, and then you have an end do. So you've got a do and an end do, and that's, you know, like I said, that's the same as the curly braces in C or C++. So now for the schedule thing, there's different types of schedules, and the couple of different types are static, dynamic, guided, or runtime. And then you see there's also this no wait. So in C, it was at the end of this list in the pragma. In Fortran, it's right here. If you specified no wait, then the threads don't synchronize at the end of the loop. So if they wait, then they all wait for each other to finish the loop before moving on. If you have no wait specified, then they just keep going. If they're finished and all their buddies aren't finished, that's okay. They're just going to keep going. Okay, so in loop scheduling, the default scheduling mode is determined by the implementation. So that is implementation specific. I think a lot of the time it is static, but like I said, it's implementation specific. So you can't depend on what it is. So static scheduling means that the ID of the thread that's performing a particular iteration of the loop is a function of the iteration number and number of threads. So it's always going to be the same thread that performs that particular iteration for a given number of iterations and number of threads. This is statically assigned at the beginning of the loop. And you could have a load imbalance problem if your iterations have different amounts of work that they're doing. But it does have a low overhead, so that's nice. So dynamic is the assignment of the threads gets determined at runtime in a round robin fashion. So basically what happens is the scheduler says, okay, here's some work for you and you and you and you. And then they come back after they've completed their current work. They come back and they say, okay, I'm ready for more. And they get more work. So this is actually a really good way to sort of do some implicit load balancing. But it does introduce a little extra overhead because they do have to keep coming back and being assigned more work. Okay, so another thing that we didn't really mention here is you see this, there's also this thing called chunk. And what that is that's like the size of the piece of work that you want to give them, like the number of iterations. So let's say you have to do 1,000 iterations, you have 4 threads. You could give them like 10 iterations to do at a time, something like that. And that would be what's called chunking. So if you don't do chunking and you're doing static scheduling, then the size of the chunks is just going to be the size of the loop divided by the number of threads. And there's going to be the number of threads chunks. And it's very low overhead. If you do chunking with static, so then your chunk size is C, then the number of chunks is going to be N divided by C. So like I said, if we had, we have to do 1,000 loops and I say, I want my chunks to be 10, then there's 100 chunks available. Okay, and that's also pretty low overhead. And that's called, that you can think of that as being interleaved. So what that is that, the first process does the first 10, the second process does the second 10, the third process does the third 10, and then they do a round robin and they come, well, it's not a round robin again, but they come back, they just press thread 0, thread 1, thread 2, thread 3, thread 0, thread 1, thread 2, thread 3. Now then dynamic, you can do no chunking if you want to, and then your chunk size is going to be the size of the loop divided by the number of threads. And so there's going to be P chunks. So that's not a whole lot different than doing a static chunking. If you do dynamic and you choose a chunk size, then your number of chunks is again going to be the number of, or the size of the loop, so the number of iterations divided by the chunk size. And it has kind of high overhead, but it's dynamic. It's gonna probably be more efficient especially if there's kind of a difference in the amount of work on each iteration. Because it'll, like I said, it'll kind of do an implicit load balance. Okay, so now guided This is where you kind of give it advice, but then it sort of will figure it out itself. So it has a high overhead, and it's optimized, but it does have this high overhead. And then runtime is you just set it by an environment variable. So if you can't decide, oh, should I do static or dynamic, or what should I do? You can put off that decision until runtime, and you can do it differently on different machines or in different cases. Just set it with with the environment variable. So you might be wondering about, okay, this is great, but what kind of loops are parallelizable? So yeah, unfortunately, not all loops are parallelizable. So here are some requirements. So in order for a loop to be parallelizable, the number of iterations has to be known upon entry, and it has to not change. So this is like your typical for loop. So, for I equals 0, I less than n, I plus plus. That type of for loop, probably parallelizable. If you have a loop that that has something in it, like let's say you're looping, but the loop is actually has to do with like some kind of measure of error, let's say. So there's a lot of while loops, like conditional loops, that are like this. So let's say I'm doing I'm doing some kind of an iteration, like I don't know, a Lanczos iteration. Let's say it's a linear algebra thing. I'm trying to reduce the error of my. So actually, this is very common in something like nuclear physics. You're trying to like find what is the energy of this nucleus. Okay, so you know the error, or you have some kind of way to calculate the error. And so you just keep iterating to get closer and closer to the right answer until your error is below some kind of threshold. Okay, well, that is a conditional loop where you don't actually know ahead of time going into the loop how many times you're going to have to run through that loop. And so pretty much any loop that is formulated as a while loop is a loop like this, and it's going to be not parallelizable. Okay, another type of loop that OpenMP just can't quite handle is an iterator loop. Like if you're iterating over a list in C++, OpenMP just, it can't really do that. So another important thing is that the iterations have to be independent of each other in order for your loop to be parallelizable. Okay, so this thing I was talking about, where you're finding the error, you're doing this iterative process to improve your result. Okay, the thing is that the next iteration depends on the values that you get in the current iteration. So those have to be done in a sequence. So they're not parallelizable. Okay, another thing is data dependence, and this is related. This is kind of the same concept. If there's something that in this next iteration that depends on something in a previous iteration, then we have to do them in that order. So one trick that I read, which I thought was super clever, is if a loop can be run backwards and give you the same results, then it is almost always parallelizable. Okay, so like if you think about this conditional loop where you're iterating and you're trying to reduce the error, you cannot run that loop backwards. So of course it's not parallelizable. Okay, I think I saw I might have a question, so let me see. Oh, a link to the slides. Okay. Let's see. Perhaps someone else can. Oh, thank you, William Thatcher. Thank you very much. I appreciate that. Okay. So before I go on, are there any questions about what kind of loops are parallelizable or parallelizing loops? To answer about the Google Doc, so you need to be logged into your Berkeley Lab account in order to be able to view it. Okay, well, I'm going to assume that means everybody understands what I meant. Okay, so here is a loop. We're going to see if we can parallelize it. Okay, so we're going to do Gaussian elimination. Anybody know what that means? Anybody not know? Probably people don't necessarily remember this from linear algebra. Okay, do you remember in math class, like in high school, algebra or something, where you would have these systems of equations where it'd be like, I don't know, 5x plus 2y minus z equals 3, negative 3x plus 7y plus 10z equals 20. I'm totally making all these up, right? Then there would be a third equation with x, y, z. Let's say x plus y plus z equals 5. Okay, and then you're supposed to solve for x, y, and z. Do you remember doing that in high school? Sort of? Are you trying to block that memory? Maybe? Okay. So, okay. Do you remember how you would do that? Just in principle, like how you would do that? What would you do? Reduce to echelon form. Okay, that's good, but that's kind of a fancy way of saying it. So what did you do? You would take those and you would eliminate, yes, elimination. That's what I was looking for. You would eliminate one of the variables. So let's say you would eliminate x. So you would take the first two equations and you would take a multiple of one and subtract it from the other to eliminate x. And then you would take the second and third equations and you would take like a multiple of one of them, or maybe the first and third, I don't know. Depends on how you chose to do it, whatever was easiest. Anyway, you would eliminate x. So then you end up with two equations in y and z, right? And then you would take those and you would eliminate y, let's say, by subtracting a multiple of one of them from the other. And then you would be left with an equation of z equals, you know, some multiplier times z equals some number. And then you would just divide by whatever that multiplier was of z, and you would have a value for z. And then you would go back in and you would back solve, right? So then you have that equation of y and z. You would substitute z in, and you would have y plus a number equals a number. And you would, you know, use algebra and you would solve for y. And then now you have y and z, and then you go back in and you substitute them into the first equation. And so you have, you know, multiple of x plus a number plus another number equals another number. And then you would solve for x. Okay, so what you actually did when you do something like that is Gaussian elimination. You just didn't call it that. Okay, a Gaussian elimination, instead of saying 3x plus 5y minus z, we have a matrix of numbers. So 3, 5, minus 1. And then we have x, y, and z that we're going to multiply this matrix by. So we have a 3 by 3 matrix because we have 3 unknowns and 3 equations. And then we have on the other side, we have B, which what we call B is our solution of vector. Okay, and so that's Gaussian elimination. Does everybody kind of understand that? Now, sort of, a little bit. Okay, so that's what we're doing here. So in this case, so I is like, which variable are we going to eliminate in the rest of the equations? And J is like iterating down the rest of the equations. And K is iterating across where we're doing this subtraction, okay? So let's say we're gonna do the 0th. So the top row, we're gonna use that to eliminate the first column on everything below it, okay? So we calculate this ratio of the coefficient in that very corner there to the coefficients in all of the subsequent rows, okay? So that we can subtract that multiple of the first row from the second row, the third row, as appropriate, okay? And then this part here is subtraction. It's doing that, okay? Here's an illustration that might help. So yellow, this is what we call the pivot row and column. So this is the one that we're going to subtract a multiple of this from all of these rows in order to eliminate everything in this column here. Then after we're done with that, then these are all zeros actually. And then but we're not dealing with any of this anymore. We're down to this part. So then we're going to take this second row. See here we're eliminating the y, right? We're subtracting a multiple of this from every row here to make all of these yellow ones here, make them into zeros, okay? And we keep going and we keep going until we get down into here. So the I loop is what indexes our pivot row or column. And then J and K is how we iterate across here. Okay, makes sense? Or no? Or no? Okay. Any questions so far on Gaussian elimination? Okay, so let's talk about can we parallelize this? So let's talk about the I loop. So the I loop is the pivot row and column, right? So we know, so it has a constant number of iterations. It's n-1. We know that from the beginning. But the iterations do depend on each other, right? Because here, after I eliminate this column, that changes the values of everything in this row, right? So I can't do this one before I do that one. So this is actually a case where that rule where can you do it backwards? No, you can't. You can't. I mean, okay, you can always do Gaussian elimination backwards and develop a lower triangular thing instead of an upper triangular thing, but you're not getting the same. You're not getting the same values. You're not getting the same answer from each loop. So that's what I mean in the sense that you can't do it backwards. But sure, in principle, you can do Gaussian elimination in any order of any of the rows. It really doesn't matter. Okay, so then let's talk about the inner loop. So the inner loop has a constant number of iterations, n-I iterations. So that's constant for a given I. And that's what we need. Going into the loop, we know exactly how many iterations. So it is constant effectively, even though it changes for every I, but it's calculatable on the entry into the loop. And those iterations can be performed in any order, because if we go back here, okay, if I'm trying to zero out this number, does it matter whether I've zeroed out this one first or not? It doesn't matter, does it? These are independent. Subtracting this row from this row and subtracting this row from this other row, those are completely independent operations. Okay, so that's why that loop is parallelizable. Okay, then last but not least, we've got our innermost loop. It's their K loop. And so that has n minus I iterations. So again, constant for a given I. And they can be performed in any order. So the K loop, in the K loop, we're iterating across entries in a given row. So does it matter if I subtract a multiple of this row from, or this, I should say this value from this value first, or this other value from this value first? Like, it doesn't matter, right? You're still gonna get the same answer. So that means that the K loop is parallelizable if we wanted to use that one. So that's great news. So we can use either of these two loops, the inner loop or the innermost loop. We can parallelize it with OpenMP. Okay, so here's my new code. This green line here, Pragma OMP parallel 4, that is the only thing that I've added to my code to parallelize it. You can combine the parallel and the 4 into a single pragma, just FYI. So that's pretty cool. I've parallelized my code with one line. I added one line to it. And that's the really cool part about OpenMP. I mean, think about if you were trying to parallelize this with MPI. It would be super tricky. I don't even know how I would do it. There are like paid experts who do that sort of thing for a living. But here we can just, boom, we just put it in there. We just added one line and suddenly we're parallel. Now people will ask me, okay, you said we could do the you said we could do the J or the K loop. So why did you pick the J loop? Well, the reason I picked the J loop is there is some overhead in creating and destroying threads. So if I pick this place here to create threads for this loop, then I'm doing it basically, let's see, I'm doing it, effectively n squared times, n squared over 2 or something, right? Because I'm going, it's going from I to n, effectively. So that's why I chose to do it there, because if I did it here, then I would be doing it many, many more times, right? Because I'd have to do it this n squared over 2 times, and then another n over 2 times. So n cubed over 4 times or something. I would have to, roughly, give or take, I would have to create and destroy threads. So that's why I chose to put it on the outermost loop. But you could certainly put it on this loop. And if, if somehow this index were pretty small, then it's probably more worthwhile to put it on the inside. That's all. Okay. Let me see if I got this right. Oh, I think I was thinking a little too hard about it. So let me try that one more time. I only have to create n times here, whereas on the inside I would have to create n squared times. Thank you, Rebecca. Okay, so because I'm just doing this I loop n times effectively, or n minus 1, something like that. So I'd only have to do this n times. Whereas on the inside here, I would have to do it n squared times, n squared over 2. That's what it is. Thank you. It was not as complicated as I was thinking. All right. So are there any questions about Gaussian elimination and how we just parallelized it in one go there? No, everybody got it because it was just so great and so clever, and everyone here is so smart. I love it. Okay. Well, if there are any more questions, I'm happy to answer them. Okay, so the next thing is called sections. So this is a non-iterative work sharing construct. So what you're doing is you're dividing the enclosed sections of code amongst different threads. And the section directives are nested within the sections directive. So here's what it looks like. So Pragma OMP sections, you have a section. So this is plural with an S on the outside. And then these are singular section on the inside. And so you can create as many sections as you want. And then of course with Fortran, it's OMP sections and then OMP end sections at the end. Personally, I don't see a lot of value in sections. The problem is, let's say this is my code and I have 2 sections. Okay, that's great if I have 2 threads. But if I'm working on a machine like Cori that has 68 cores, then it's entirely possible that I could have 68 threads. So what that means is that I'm going to have 2 threads that are doing something and 66 threads that are just hanging out waiting for those other threads to do their thing. So that's why I don't personally use sections, and I would not really encourage you to. But there can be times when sections is a good idea, and it may be something where that's the best you can do in a place that would otherwise have to be completely serial. So it just kind of depends. I'm not going to say never use sections, but I personally have not really ever seen a compelling reason to use them in my own coding. So here's an example. And the thing is, this example is something that you could better do, with a for loop, right? So maybe I've got 2 sections here where I want to update some variables, right? But this would actually be way better done if we were just going to use a loop, right? Just a for loop, a parallel for. This would be done in a jiffy instead of having these 2 sections where you're doing these 2 separate things. So anyway, just goes to show you not much value in this necessarily, but there could be cases, like I said, that things I haven't done before, where there are conditions where this would work better. I don't know. Okay, so now let's talk about synchronization. So sometimes you might want to make sure that your threads execute some regions of your code in a certain order. So it could be that there's one part that depends on another part being completed, or there could be things where only one thread needs to execute a section of code. So for example, I/O, maybe you don't need all your threads printing out. Maybe you just need one to do it. So there are these synchronization directives that we're going to learn about. So critical, barrier, and single. So critical specifies a section of code that must be executed by only one thread at a time. And in C or C++, it's just pound pragma OMP critical. In Fortran, it's 2 things, right? The critical and end critical. And you can give your critical section a name, and you probably should, especially if you have more than one, because the names are global identifiers. So any critical region that has the same name is considered the same critical region. So if they have no name, then they're all the same critical region. So if you had 2 threads that are going through 2 completely different critical regions, they would still both have to stop, and only one at a time would be able to run. Okay, single is another one. Single is where you only let one thread execute some part of your code. This is useful for thread unsafe parts of your code, like I/O, like I was saying, if you're printing something. Also, sometimes if you're reading or writing from a file. And then, you know, here's our syntax. Now, a lot of times people will confuse critical and single, because they're very similar. Critical is one at a time goes through this part of your code. So everyone goes through it, but just one at a time. Whereas single is only one thread executes it. Now, a single is a lot cheaper than a critical. So you don't want to confuse them if you don't have to. You want to use a single when you can, and a critical only when you really need it. Okay, then last is barrier. So a barrier synchronizes all your threads. So your threads, they'll reach this barrier and they'll wait until all of their friends have gotten there too. And then they'll resume executing following the barrier. Now, you could have a very complex code that has sort of different paths for different threads, and that's fine, but you got to make sure that the sequence of work sharing and barrier regions that each thread encounters are the same. So they could encounter a barrier on a completely different branch of the code, but it needs to correspond. You know, they all need to have the same sort of experience of reaching the same barrier at the same time, even if physically the barrier that one thread reaches is on a different line of the code than another one reaches. That sounds a little weird. You may not quite understand what I'm saying, but anyway, that's sort of the idea. Okay, so now we'll talk about reduction. So this is the same idea that we had with MPI reduce, but only it's OpenMP. So a reduction, you know, you're reducing your list of variables into one using an operator. So maybe the max, the min, the sum, the product, that sort of thing. So the syntax is pretty simple. Pragma OMP reduction, and then whatever your operation is, a colon, and then the list of all the variables that you want to reduce on. Usually, you know, it's just one or something, but you can reduce on a bunch of different variables at the same time with the same operation. So these are your choices. So, you know, in C or C++, we've got plus, minus, product, and, or, no, that's or. I don't know what all these are. And max and min. And similarly in Fortran, we've got similar choices. Okay, so before I move on to variable scope, I want to make sure that we don't have any questions waiting along. Oh, if you use minus, which doesn't satisfy commutativity, how do you guarantee consistent result? Oh, but it's everyone is minusing. So -2, -3. And that's the same as -3, -2. So it does sort of. So is critical like making a code block and its data essentially thread safe? Yes, it is. It's making it thread safe. It's forcing thread safety. Good question. Okay, so then let's go on to variable scope. So We're going to talk about variable scope, scoping clauses, and common mistakes that people make. Okay, so variables can be shared or private within a parallel region. So what shared means is that there's one copy of the variable and it is shared between all threads. So it is in a single memory location that's common to all threads, and it's accessible by all threads. A private variable, on the other hand, each thread makes its own copy. And really the private variables exist only within the parallel region. And then when you get out of it, yeah, they don't exist anymore, really. So by default, and I kind of question the judgment of the OpenMP ARB at times for this decision, but all variables are shared by default, except the index values of parallel region loops. Those are private. Those are private by default. A kind of a special sort of a private. Local variables and value parameters within subroutines that are called within a parallel region, those are private. So if I have a parallel loop and within that loop I call a function, and then within that function it creates variables, those are all private variables. And then any variables that are declared within the lexical extent of the parallel region, those variables are also private. So if I have a loop that is a parallel loop, and then inside of it, I define a new variable, that is a private variable. Variable scope is the most common source of errors in OpenMP codes. So you can really paint yourself in a corner and really get some bad results that are really insidious and hard to find if you don't have your variable scope correct. And then also it can really also impact your code's performance at times. But the worst part is you can just get these insidious errors where sometimes you run into this problem and sometimes you don't. And you can't predict it exactly and you don't know what to do. So let's talk more in detail about how you do this. So shared variables, so you remember at the very beginning we saw the parallel section and we saw there was like shared and private, okay? And so your shared variables, you just put them in a list. But by default, all variables are shared unless otherwise specified. All threads can access the variables in the same location in memory. And you have to really be concerned about race conditions or other problems if your access to a shared variable is not carefully controlled. Private is another one, right? So the variable really exists only within the parallel region. Now, I told you that the loop index of a parallel loop is going to be private, but it's a slightly different thing than this. But it is basically private. So at the start of the parallel region, whatever variables are in that list, they're undefined. So they don't have a value yet. And then at the end of the parallel region, they don't have a value anymore. Now, if you want to start them off with defined values, then you use something called first private. And that will make the private variables initialized to be the value that was held immediately before entry into the parallel region. And if you want them to end with a defined value, then you use last private. And that'll set the variable to the value set by the final iteration of the loop that you were in. Okay, so here's some really common mistakes. So the most common mistake is a variable that should be private is public, and something unexpectedly gets overwritten. And the solution to never having this problem is to explicitly declare all variable scope. Another problem you can get is a non-deterministic execution. And this is different results from different executions. And again, this is often caused by variables that should be private, but they are shared or something like that. And then race conditions, you know, that's another sort of a symptom of this that you can see. So look out for overriding of a shared variable. I mean, that's the 99.9% of the time there's a shared variable. It gets overwritten somehow. It shouldn't be, but it does. It should be private maybe. You can use a tool such as Cray Reveal or Parallelware Analyzer to analyze your loop and fix it and tell you what things need to be private and what things need to be shared. Okay, so here's my new Gaussian elimination. You remember, we all know Gaussian elimination now by heart, right? So can you spot the mistakes? Do I have any mistakes here? Maybe it's perfect, I don't know. Anybody see any problems with my variable scope? Does it all look perfect? Is it perfect? I mean, usually, I mean, everything I do is so great and perfect. Am I just fooling ya? Oh, ratio, yes, ratio will be overwritten. Okay. That's right. So here I have defined ratio here, and it's shared. Oh, well, I just accidentally clicked and did my answers for you here. But yes, ratio is one of the 3 variables that are shared. And if we have a smart compiler, it may actually completely optimize out K, and so we won't be impacted there. J is going to be actually, it's going to be considered private because of this pragma. So actually J is going to be okay, but ratio and K could lead to some problems here, right? So let me explain a little bit more. So let's say that ratio is a shared variable. Let's say I'm a thread and you're a thread. Okay. So first I compute the order that it works for us, right, is we compute ratio, and then we use ratio in these lines here with A and B, where we're going to multiply each entry of the row by our ratio, and each entry of the right-hand side vector by the ratio. Or, I mean, we're going to subtract. Anyway, so let's say that I set ratio to be my value of ratio. And then I start in on this, okay? Meanwhile, you're computing, you're just a little bit behind me, and you compute ratio, and so now you set ratio to your value. So what's going to happen here is that now I'm going to be subtracting a multiple of your ratio from my row when I need to be subtracting a multiple of my ratio. So then we're going to run into all kinds of problems. It's going to be a disaster. So yeah, that's good. That's the problem. Now, like I said, if we have a good compiler, probably K is going to be optimized out. It's just going to do all these rows at once, so we'd probably be okay. But we would still have this problem with ratio. Okay, so here's how I would solve this problem. In my private OMP parallel for, I would just add what I want to be private, so J, K, and ratio. And then what I want to be shared, which is going to be A, B, and N. And I add this default none. And then what that does is when I compile, if I accidentally forgot to define something here, then the compiler would say, hey, you didn't define variable Q, so go fix it. And then that way I would never run into this kind of a problem. That makes sense? Any questions?
Sorry, can you just explain real quick the difference between the problem with the ratios? I'm still having a little trouble getting that.
Okay, yeah, sure. So the problem with the ratios is if we have a shared variable called ratio, okay, and let's say that you and I are two threads, okay? So let's say I'm on, so J is what we're parallelizing over, right? So let's say for me, J equals 5, and for you, J equals 6. I don't know. Okay, so then I'm going to compute this ratio of A 5I, right? And you're going to compute this ratio of A 6I. Okay, and then we're going to both go into this loop, and we're going to multiply that ratio by each entry in our respective rows, and subtract it from that, right, from the corresponding row, right? So this is the pivot row, and then this is our row that we're doing, right? So the problem would be, okay, let's say I compute my ratio, okay, and then I get started here and I start doing stuff, okay? You compute your ratio and you overwrite mine in the variable, in the space where that variable is stored, okay? So then what's going to happen is then I'm going to pick up your number now, and I'm going to start multiplying by your ratio rather than my ratio that I should be multiplying by. So then I'm going to get the wrong answer. Okay. That makes sense?
Got it. Yeah, no, that makes perfect sense.
Okay, cool.
Thank you.
Yeah. Okay, so like I said, if I set default none, the compiler is going to catch any variables that aren't explicitly scoped. So if there was some variable that I forgot about here, which I don't think I forgot about any, but if I did, it'll say, hey, what about this variable? You didn't scope it. So that's what you want to do, though. You always want to scope all of your variables. It's just good programming practice, and it helps make sure that you understand what's really happening here. Okay, so let's talk about runtime library routines and environment variables. Okay, so here are a couple of OpenMP runtime library routines. There really aren't that many of them, and this is most of them, I believe. So OMP set num threads. So you can actually set the number of threads that you're going to use in the next parallel region of your code. You have to call this from the serial portion of your code before you begin. Okay. I have never used it. I don't think I would ever use it, but you can. Okay. In OMP get num threads, this tells you how many threads that are currently in this team that's executing in parallel. So it's a lot like MPI com size. It's a comparable thing. So that makes sense. That's something that you would maybe need to use. And then OMP get thread num, and so that's the rank of your thread. And we saw that at the very beginning in that hello world code. And so the thread number is going to be between 0 and OMP get num thread -1, right? So like if there's 5 threads, then it's going to go from 0 to 4. Okay, then there's these environment variables, and this is where you want to set things usually. So OMP schedule. So remember before I said, you know, if you didn't want to figure out what scheduling you wanted to use, you could just set it with an environment variable. And so this is an environment variable that you can use. So it determines how the iterations of loops are scheduled. So you can set like dynamic and a chunk size of 4, for example. And then also OMP num threads. This is an environment variable that sets the maximum number of threads. And this is how you probably would actually do it rather than in this, you know, OMP set num threads within your code. Like, I don't know why you would do that. You'd want to set it to depend on what machine you're running on. So 4 threads might be really great for some machines, like a quad core machine. And then 68 threads might be really great on the Core EKNO nodes. All right, so how do we use OpenMP? You remember I told you you can do conditional compilation. You can write a single source code that you can use with or without OpenMP, and your progmas, they just get ignored if you've disabled OpenMP. Okay, but what about these OpenMP runtime library routines? Well, there's a little macro called _OpenMP, and it's defined if OpenMP is available. So you can just use that to conditionally include OMP.h and to redefine runtime library routines if OMP.h is not included. So here's an example. So if we're compiling with OpenMP, that's what this _OpenMP means, then let's just include OMP.h header file. Otherwise, I know I want to use this OMP get thread num thing. I'll just define it to be 0. Because that way I can use it, because somehow I need to know what my thread number is somewhere in my code. So if there's no threads, then my thread number should be 0 because I'm the only thread, right? That makes sense. So that's an example of conditional compilation where you can include these conditions, these definitions, if OpenMP is defined or undefined. Okay, now how do you enable OpenMP in your compiler? So just like every compiler that I know of anyway supports OpenMP directives. I mean, today, even your desktop machine has multiple cores. So OpenMP is pretty widespread in these compilers. So if you're using the Intel compiler, which is what we are using on Core, by default, the programming environment is the Intel programming environment. So underneath the CC compiler wrapper, it's invoking the Intel compiler ICC. So you would use this flag -q OpenMP. Now, if you're using the GNU compiler, then that's -f OpenMP. PGI, it's -MP, and the Cray compiler is -h OMP. So how do we run our codes with OpenMP? So we just set these OpenMP environment variables in our batch script. That's the easiest way to do it, including a definition of OMP num threads in your script or on your command line. So if I wanted to run a code with 8 MPI processes and 4 threads per MPI process on Cori, so then what I'm going to do is I'm going to export these environment variables, and I'm not going to go into what exactly all these mean because it really doesn't matter. But then that's how I'm going to run it. I'm going to set OMP num threads to 4, and then I'm running on 8 processors. And then this part here has to do, this -C8 and the CPU bind stuff has to do with affinity and making sure that your threads don't all just kind of crowd onto like one core and run really inefficiently. Just kind of spread them out. But it's not that important for today's purposes. Then I'm going to run my program. What I always do, because I have, have a memory like a sieve or like a fish or something, I just use this JavaScript generator that NERSC has. And then it tells me all the right things to do, and I don't even have to think about it. Let's see, I think I can show it to you. Yeah, here it is. And so I can just say, I want to use one node, I want to use 2 MPI processes, and I want to use, I don't know, 16 threads. And then it generates a script for me. And here it is. And so then I just copy and paste the script into my file. And I don't even have to think about it because I don't even know what any of these things mean. I don't know why that's C minus 32. I have no idea. I don't understand what it means. But I don't have to understand that because I can just use this JavaScript generator. So let's get back to this. And maximize, I guess. Oh, that's weird. Oops. Okay, so are there any questions so far? Does anybody have any questions before we go on? All right, well, I'm going to assume that we don't have any questions then. So let's talk about computing pi with OpenMP. Okay, so let's think about our original DARTS program and how could we exploit shared memory parallelism to compute pi? Okay, what is like the best kind of algorithms for shared memory parallelism? Anybody have an opinion about that other than me? Loops. Shared memory parallelism and loops, they're just like best friends, like BFFs forever or something. They just love each other. So what we should do then is parallelize our loop with OpenMP, right? Our loop for computing DARTs. Okay, so what kind of pitfalls might we encounter if we do this? Anybody have any thoughts? You remember our pseudo-random number generator? Yeah. You know, it has that variable that it uses to store. Yeah, you get the same number. Yeah, and you'll get some weird overwriting things. It has that one variable. It's like random last or something that it uses to store the random number. Yeah, so you'll everybody might be sharing that, and so it's not thread safe, that's for sure. So what could we do there? I mean, there's a couple of different things, right? We could make that, we could kind of make that like a critical section, where every time that you make every time that you roll the dice there, so to speak, generate a random number, that could be a critical thing, right? But that's going to be really inefficient, because it's like somebody said, it's like making it thread safe. It does make it thread safe, but then it's a sequential operation effectively, because only one thread can do it at one time. So another possibility that we might consider would be to just take that number that, what was it called? Random last is what it was called. Take that random last and make that into a private variable where each process has its own copy. So that's probably the better choice. Now remember, though, that last time we had this problem where they all started, random last started, it was 0. And so then you're essentially repeating the exact same random numbers across all of the different processors, or in this case, threads. And so you're doing the same amount of work for a fraction of the same accuracy. So we'll also have to kind of change the seed, the starting seed for each process. So those are all the things that we had to think about in order to do this. Let's see, are there any other things that we might have to consider, or have I thought of everything? Any ideas? All right, I'm going to assume that means I thought of everything. Oh, we're not going to hybrid programming yet. Okay, let's make this small. And let's go to here. Okay, so I'm going to go to Scratch. What was my thing? Okay, CD, developing, okay. What do I got? Okay, I've got darts. Okay, so I'm going to copy darts.c to darts OMP.c. Okay. So the first thing I'm going to do is include OMP.h. Okay, that way I won't forget to do that, because I always forget. Okay, so let's see. This is the thing right here. This needs to be parallelized. Okay, so this is a for loop. So we need to have a parallel section. So let's see, pragma OMP parallel. It's going to be this whole thing right here. Right? Because calculating pi, we can do that after we don't need that in parallel. That should be serial. And printing it out should also be serial. So this is going to be our parallel region right here. Okay, so now there was something that we talked about. We need to decide what variables we want to be shared, not shard, shared, and what we want to be private. Oh. Okay, so now one thing that we need to be private is random last, right? We discussed that. Random last needs to be private. Is that what it was called? I'm suddenly having my doubts here. Let's just look. Yeah, random last. Okay, good. I remembered the name correctly. Okay, what do we want to be shared? Okay, so a lot of these things that are kind of constants, we can have them be shared, like r squared, num trials. Okay, what else do we need to have private though? X and Y? Because I don't want, if you're writing X and I'm writing X, we might get, ooh, how about schedule? Oh, okay. Yeah, so we haven't done any scheduling yet, so we can figure that out in a few minutes. That's a good question. Yeah, we want I to be private. It's going to be implicitly private when we make that for loop be our parallel loop, but it's good to do it. Okay, and then what else? Anything else needs to be private? Okay, so something that we're going to do is this is going to be a reduction, right? You see how this is a reduction? Yeah, okay, maybe not. Okay, so NERSC, right? I'm going to calculate my value of NERSC. You're going to calculate yours. And then we're going to add them together, right? Like that's the final point, right? Is that we add together all of our values together, right? All the dart throws that I do, all the dart throws that you do, we have to add them all together. So that's going to be our reduction variable. And it needs to be a shared variable, I think. Yeah. In order for it to be do the reduction. Okay. You know what? I'm going to look at my reduction because I never get these right. Reduction. Okay. Y'all, I may have to cheat because I don't remember how I did this before. I'm going to cheat. Let me cheat. I always teach it in a different way, and then I always do it in a different way. So let's see. Cat. Darts, sweet. Wait. Yeah, darts, sweet. C. Darts, OMP. Let's see. Let's see. What did I do? Yeah. Oh, okay, so I did it a different way last time. I always do it differently. So I did make it a critical region for those, but I don't want to make a critical region this time. I don't like critical regions. Okay. Yeah, okay. So, prime OMP for prime, yeah, okay. Okay. So here I'm going to put that pragma OMP4 and then reduction plus colon NERSC. Just make this a little bit prettier. Okay, so that's how I'm going to do that. And then I want to set random last equals OMP get thread num. I think that should do it. Let me just make sure that I got OMP get thread num correct. Yep, OMP get thread num. Okay, so now somebody asked me about the schedule. So we could try scheduling this for a loop. So let's see what our different options are. So we could do static, dynamic. If we're going to do that, then we would put, oops, that's the Fortran. We would put the schedule. And then, yeah. Should we schedule it? Anybody like want to schedule it? Or should we just let our OpenMP implementation do its thing? I don't really care. No, I see somebody shaking their head. Is that a no, like don't let them do it? Or is that like a no, don't schedule?
Schedule it.
Oh, you want me to schedule it? Ah, okay. Okay, so we'll do schedule. Okay, so let me put it, let's see, parallel. Schedule. Okay, what kind of schedule do you want? Anybody? Anybody? Dynamic? I like dynamic. Let's see if we can get it going. Y'all are challenging me here. Okay, dynamic. Do we want a chunk size? Do we want a chunk size? Sure. Let's have a chunk size of 100. Okay, this line is awfully long. You know, I can just do this to continue it so we can see everything. Okay, does that look good? Is there anything I'm missing? I'm probably missing something. Because I've written a lot less OpenMP than MPI. So, oh, you know what? I'm so out of it. This is what I missed. This belongs here. Oops. And I need a space here. Or I'll just go like that, sure, why not? That's what I was missing. I knew there was something that was not right. And that was that I put that schedule in a place where there's nothing to schedule. I'm sure the compiler would have told me about it. Okay, anything else? All right, well, shall we go for it? Let's go for it. Okay, thumbs up. TC minus QOMP darts OMP.C. Not C, O, darts OMP. All right, recross your fingers. Because I didn't do this right. It's not QOMP, it's QOpenMP. There we go. Oh boy, it compiled. Okay, it's a little scary. Okay. Okay, well, we'll just cross our fingers that that it's going to actually run. So let's try it. Okay, so let's say export OMP num threads. Let's go for 1 right now, huh? 1. And then let's run it. So when we're running an OpenMP code that does not have MPI in it, we don't actually need to use srun. So darts OMP. Oh, hey, look at that. We got the right answer. Okay, with 1 thread. Shall we try 2? Let's go for glory here. 2 threads. Okay. Ooh. Okay, not so good. Let's try 4 threads. Huh? 3.1413. That's very strange. That's actually better than the 2. I have no idea what's going on. Try 8. Huh. Okay, let's go crazy. Let's go 16. Okay, that's like way worse. Yeah, I don't know exactly why this is pretty wrong. I would like to blame the pseudo random number generator. That's what I would really like to blame. But I suspect that's not really it. There's probably some other problem that I just can't really see right now. Anybody have any ideas of what I did wrong? Probably not. Okay, well, I guess we should move on. I apologize for not getting this one quite right. But it just kind of shows you how insidious it can be, in my defense, how insidious it can be. Okay, so let's go on to talk about hybrid programming. Okay, hybrid programming. Yay, hybrids. Probably data or less sizable. I mean, yeah, so I would expect Yes, I would expect my quality of answer to go down somewhat, but not quite that drastically, because my pseudo-random number generator is pretty sad. So let me just show you. My pseudo-random number generator has a period of 714,025. And I'm asking it to run 1,000,000 times. So about almost 30,000 of those million, 300,000, almost 300,000, sorry, of those million times. So 30% of those times are repeats. So I'm not going to get a particularly high quality of random numbers because they're repeating. And then if I set my my seeds to be different numbers, so I set them to be 0 through 16. If those are evenly dispersed throughout, then I'm in good shape. If they're not, then I may have even more duplicates. But it's hard to know. Okay, so let's go through this here. Can't believe it. We've been having so much fun, y'all, that almost time. Okay, hybrid programming. So let's talk about hybrid programming. We're going to cover motivation and considerations we should think about when we're designing our codes, MPI threading support, kind of designing hybrid algorithms, and then hopefully sort of an example. Okay, so multi-core architectures are here to stay. So we talked about this earlier. On the macro scale, it looks like a distributed memory architecture suitable for MPI. On the micro scale, each node contains multiple cores and shared memory, so it's great for OpenMP within a node. So obviously is, like that meme where it's the little girl, why not both, right? ¿Por qué no los dos? So the obvious solution is to use MPI between nodes and OpenMP within nodes. And this is what's called a hybrid programming model. Okay, so that's really exciting, but is it always better to use hybrid programming? And the answer is no, not always, especially if it's poorly programmed, don't do it. It also kind of depends on the architecture. And so basically you can think of this as like an accelerator model. So in an OpenMP parallel region, you're using the power of these multi-cores. In a serial region, you're not. You're using only one processor. So if your code can exploit threaded parallelism a lot, for whatever value of a lot you think it should be, then try hybrid programming. So when you're doing hybrid programming, some things to think about include, are your communication and computation discrete phases of your algorithm? I mean, this is not like a right or wrong thing. This is like thinking about, is this true or is this not true? Can communication and computation overlap? Because if they can, then that's really great for these types of algorithms. If not, you can try to think of ways that they can, but it's not the end of the world. You also want to think about communication between threads. Like, how would you want to do that? Would you want to communicate only outside of the parallel regions in your code? Would you want to like have a manager thread that's kind of like responsible for all inter-process communications? Would you want like some threads to perform inter-process communication, or would you just want to be like, hey, let's just go for glory. Let's have everybody communicate like a free-for-all communication, like Wild West. So in MPI, the MPI 2 standard defines 4 threading support levels. So the first one is 0. MPI thread single. And so in that you only have one thread allowed. Whenever you're doing MPI, you can't have multiple threads. In MPI thread funnel, that's number one there. The master thread is the only thread that's permitted to make MPI calls. So you can be in an OpenMP region, but only the master thread is the one that's allowed to make MPI calls. And I realize master thread is not such a great phrase, but that is what it is called, unfortunately. So basically, though, that's thread 0. MPI thread serialized is that all threads can make MPI calls, but only one thread at a time can make those calls. And then the third one, or the fourth one, depending on how you're counting, is the MPI thread multiple, and that's just no restrictions. That's like any thread can do any kind of MPI at any time. And that is the thread-safe version of MPI. And then if you just don't even, if you're using MPI 1, or if you're not using MPI init thread, which we'll see is how you initialize the threading support, then you're effectively an MPI thread single. Okay, so if you want to know like what threading model does your machine support, you can run this code on your machine. So I ran it on Corey, and I got this. So by default, the threading model of the Cray MPI implementation is level 2. Okay, I can set an environment variable to make it be level 3, but it's they say like you probably don't want to do that. Like it's risky, and it also is not very performant. Okay. So when you're going to use threading, you want to use MPI init thread instead of MPI init. And so it takes 2 arguments, required, which is what you're requesting, and supported, which is what you're getting. So required, ideally, you'll get that back for supported. If that's not available, then it's going to return the lowest level that's greater than your requirement. And failing that, it's going to return the largest level less than your requirement. I know that sounds kind of weird. Like, why would it do that? Why would it give you the greater one? Well, it wants to give you as much as it possibly can. And I don't really know of any implementations where they've like implemented 0 and 2, but not 1. Like, I don't know of any like that. But a lot of times, if you're asking for 3, they're going to give you 2. They don't have 3, or they make it so that you have to jump a few hoops to get 3 at least. So like I said with the Cray, there's an environment variable that you can set, but it's kind of at your own risk and ill-advised. So at the end of your code, you want MPI finalize to be called by the same thread that called MPI init thread. So I mean, I guess what that implies is that you can start an OpenMP parallel region and then invoke MPI. But I don't think I would do that. But you can, should you desire. Okay, so then there's these 2 querying options that are pretty useful. So MPI is thread main. It tells you whether you're in the main thread or not, and then that'll tell you, whether you should do MPI finalize from it, for example. And then MPI query thread, you're asking, hey, what level of thread support do we have here? And so this could be useful if you have an algorithm that you have some kind of special optimized version of it for the 3rd level, and so you would only use that if that was available. Otherwise, you would use this slightly less optimized version of your algorithm. Okay, so if we're in the single paradigm, then we're going to use the single pragma. Easy to remember. So if we're going along and we want to call an MPI function in the middle of our OpenMP parallel region, then this is how we would do it. We would just do a barrier. We would do OpenMP single, where only one of them is allowed in there, and then a barrier again at the end, and then we move on. Okay, so if we are doing the funneled version, then we use the master pragma. And so we didn't learn about that one, but it basically is just like, hey, thread 0 has to do this. So it's just making thread 0 do that. And so it's pretty much exactly the same as this, but just using a slightly different pragma. If we're doing serialized, then this is what we would do. We don't need a barrier at the end here because single just lets one of them through at a time. They're all going to go through one at a time. And then multiple. So there's an Intel MPI on Cori. I didn't include it in here today because I don't know. I don't think people use it very much. It's not optimized really for the machine like the Cray version is. But I guess if you really wanted to use the multiple threading model, then you could use the Intel MPI implementation. So if you're using multiple, you don't need any pragmas to protect your MPI calls because anybody can do any MPI call at any time. But there are a few constraints when you're using multiple. So the ordering of the MPI calls within each thread, but not across MPI processes, you're responsible for preventing any race conditions that are happening there. So that can be pretty tricky. Blocking MPI calls will block only the thread that is doing the calling. Multiple is not really required for most people's algorithms. Most algorithms you can write just fine without it. But if you just really want it, then I guess you should do it. So which threading model should I use? I mean, I'd give you like a very resounding answer of it depends. So the nice thing about single is it's portable and every MPI implementation supports it. But you have some limits on your flexibility. So funneled is simple, pretty simple to program, but you can get concerns about the manager thread getting overloaded. That's always a danger. Serial, you have a lot more freedom to communicate, but the risk there is like too much communication. And then multiple is completely thread safe, but limited in availability and generally suboptimal performance because there's so much work that has to go into making the MPI library thread safe. Okay, so when you're thinking about designing your hybrid algorithm, this is what, I'm a mom, so I like say this like 12 times a day to my children. Just because you can do something doesn't mean that you should, right? So just because you can communicate like thread to thread, basically, I mean, it doesn't mean that you should. So there's a trade-off between lumping messages together and having like a single overhead for a large message that gets sent and sending individual messages. So you have one big message and one overhead. With individual messages, you have a lot of little messages with a lot of individual overheads. And maybe you might have less wait time, maybe, but not always. So you just really have to think about that trade-off. Like, should you just send like a huge care package, or should you send, 12 different things and in 12 different packages? So it's kind of like my Target order. Actually, I ordered some things from Target and they sent like everything in an individual envelope or a box. And I'm like, what the heck, y'all? Couldn't you just, put them all in one big box? I would have waited another day or two for that, but no. Okay. So anyway, I guess that the moral of that story is that Target uses level 3 or something. I don't know. Anyway, another issue you really need to think about is programmability of your code. So the thing is, you may have this great idea for this genius algorithm that's going to be super performant and everything whenever you get it working. But there's always these little problems because it's complicated. So you need to, kind of balance like getting the most optimal algorithm of all times with your personal time and how long it takes you to develop that. Okay, so let's just give a little example here of mesh partitioning. So we might have a regular mesh of finite elements. That's a classic problem that people do. You have some kind of domain and you divide it up into some pieces. So when we partition it, we're going to need to communicate information about cells that are adjacent on the domain to their neighbors who might be on a different MPI process. So like, here's my illustration. So if we were just doing MPI and we had this, we had this square domain and we had all these little, pieces in our domain, we might divide it up something like this, where we would just kind of give the first processor 0, we just give it like the top quarter of the square, and processor 1 would get the next quarter of it, and, etc. And then within each of these, then our processor would divide it into, let's say we have 4 threads. So each thread would then kind of like get, a subsection of that. So they would have kind of their own domains. This is probably the way that we would organize it, but maybe we would do it vertically. I don't know. Anyway, so this is kind of like how your communication patterns might go, okay? So if you were doing kind of like the lower, 0 or 1 type of thread support, it would be this purple, right? You would have like this manager thread, and it would be sending out all the information and communicating back and forth. On the other hand, if you were choosing some, 2 or 3, you might have kind of a free-for-all where like, this processor is going to send its information here, and this one is going to send its own information, and it just gets kind of weird and kind of complicated. It just, so there's just trade-offs is just my only point. There's just trade-offs between doing these things in these different ways, and some of them are good, some of them are bad. You just have to kind of experiment with it and see how you go. So that's my advice primarily, is just experiment and see how you go. Okay, so if you really like OpenMP, there's a lot of really great resources out there. So the first one I would point you to is there's this book, and Helen He is actually in my group. She's on the OpenMP ARB, like I was telling you. And she and some colleagues, she wrote this book called the OpenMP Common Core. So it's a great book. And she gave me an autographed copy. And actually, if you were with us last week learning about how to use NERSC, Helen was the one who taught that. So you already know her. So you already know a book author. It's so cool. Anyway, so that's a really good book. There are other OpenMP books. There's a good OpenMP tutorial at Lawrence Livermore National Lab website. So they had an MPI tutorial. They also have a good OpenMP tutorial. And yeah, there's a lot of other stuff. So I got this, this one didn't become a link, but this tips, tricks, and gotchas, that's where I got the, where I read about how if you can do a loop backwards, then it's probably parallelizable. So that was super cool. Trick. Yeah, this one I thought had a great title, How to Parallelize Your Code with Ease and Inefficiency. And then if you also need a little light reading and you're you're not getting tired enough at night, the OpenMP standard is available. So you can learn all about it, fall right to sleep. And then if you're interested in hybrid programming, there's some good presentations out there. There's this best practices guide to hybrid MPI and OpenMP programming. And there was a tutorial at SC13. And this is hosted on the openmp.org website. So that's it. Oh, I forgot the last. Oh, I did. I totally forgot the last interlude. But the last interlude was put it all together and make your make a hybrid program using your MPI and your OpenMP. But we've got we've got 2 minutes left, so I don't think we'll do that unless anybody's really begging for me to do it. Then we can do it together. But I do want to talk about computing pi. Okay, so I told you, like, don't compute pi with the method darts. It's terrible. The reason that it's terrible is that its accuracy is proportional to the square root of the number of darts. So if you want a 1 decimal point increase in accuracy, you need 100 times more darts. So this is what's called a Monte Carlo method. Sometimes you may have heard that. Monte Carlo methods are great for, okay, so basically we're taking an integral, right? Because we're calculating the area. And so Monte Carlo methods are a great way to take the integral of higher dimensional functions. So this is a 1-dimensional function. Okay. Well, I guess, no, it's a 2-dimensional function. Here's you got x and y. Okay. If you have like a 10-dimensional function, it still costs n squared. Okay. Monte Carlo is constant. It's always costs n squared to get an accuracy level. So if you were using any other type of quadrature method, it would be proportional to the dimensionality of the function. But these Monte Carlo methods are just always n squared. So Monte Carlo, great for higher dimensional functions, terrible for computing pi. So don't do it that way in real life. So instead, you can look it up on the internet. You can use your programming language constant, or you can use a different type of quadrature or a power series expansion in order to get an accurate pi. But like, just don't use the method darts. The only reason we're using it today is because it's pretty easy to understand, and it's also very easy to parallelize. Okay, now random number generation. I told you I wasn't going to talk about it, but I lied because I love talking about it. So there's really no such thing as random number generation, at least in computing. The proper term is pseudo-random number generator, PRNG. So basically, it just generates a long sequence of numbers that seems random. It's kind of what I told you earlier. So the properties of a good PRNG is that it has a very long period. It's uniformly distributed, because that's another problem with true random numbers, is they tend to be clumpy. But a pseudo-random number generator is uniformly distributed. Reproducible, so that you can use it and you can actually debug your code. And quick and easy to compute. So those are kind of the 4 good properties for a PRNG. So the one that we used is a linear congruential generator. Those are known to have problems. So this one in particular has a really short period. So like I said, it's like 700,000. So when we were trying to do 1 million dart throws, 300,000 of our dart throws were repeats. So it's not uniformly distributed. In fact, it's known to have correlations. But it is reproducible. You can get the same sequence, and it's quick and easy to compute. So, but don't actually use this at home. Don't do it. It's not very good. So this is a picture of Randu, and Randu is a linear congruential generator. It was very popular in the 1970s, and they used it a lot to simulate our nuclear stockpile. So this, they discovered, okay, if you if you generate basically triplets of Randu, they are all in these planes like this. So it's not random at all. It's not distributed evenly or uniformly. And so our linear congruential generator has similar problems, although not as bad, I guess, as Randu. But kind of scary to think about our nuclear stockpile was simulated with this. Okay, so if you want to actually have a good pseudo-random number generator, the best one right now that we know of is the Mersenne twister, very highly rated. The GNU Scientific Library, it's a great library. It has many generators available, including the Mersenne twister. And also if you use the Intel MKL library, the math library, and that's available on Cori. Actually, both of those are available on Cori. You can get the Mersenne twister from that too. Now for parallel codes, SPRNG, they pronounce it Spring, is regarded as the leading parallel pseudo-random number generator. So that would be my recommendation. There is a Mersenne twister in Intel MKL that can support up to, I want to say like 256 streams of generation of pseudo-random numbers. But if you need more than that, you should use Spring. So that's it. So do I have any questions? Any final questions here before we go?
Rebecca, I have a quick question. So to somebody who's new to parallel computing, do you suggest they start with either OpenPI or the other one, OpenMP or MPI, or use a hybrid approach?
Right, so it kind of depends on what you want to do. So if you want to do parallel programming where you run across multiple nodes, then MPI, you have to learn MPI. If that's not what you want to do, you can do MPI or OpenMP. But like I said, just kind of all my answers today, right, are it depends. I don't have any straight answers, so yeah.
Okay, thank you.
Yeah. Okay, so I've got. Oh, okay. So there was a question about how does reduction work? Does it execute after the for loop for all threads that have been completed? I don't really know. That's a good question about how it works. Yeah, I actually have no idea how it works. So sorry, I can't answer your question. Okay, 2 questions for clarification. Number 1, are hybrid and heterogeneous computing the same thing? And 2, can we say CPU, GPU is hybrid programming paradigm? Okay. Hybrid and heterogeneous are not completely the same thing. So, I mean, you can do hybrid programming on a homogeneous system. So like on Cori, for example, on the KNL nodes, every node is the same, but you're definitely doing hybrid programming because you're using 2 different programming paradigms. You're using MPI and OpenMP. And likewise on a CPU GPU system, which is a heterogeneous system, yes, you are using hybrid programming because you're probably using MPI across nodes. And then within a node, you're probably using something like CUDA or OpenACC or possibly OpenMP to accelerate using the accelerator. So that's also a hybrid programming paradigm. So yes. Okay, any other questions? All right, well, I'm sure that your brains are overfilled by now, probably. So I really appreciate y'all joining me today. I had a lot of fun. I hope you all had fun. And if you have any questions, you can try and give me a holler. I'll do my best to respond. I do get a lot of emails, but I'd be happy if you sent me an email if you had a question. And also, check out these resources. I think they can be really helpful. You can learn a lot more that way.
Thank you very much, Rebecca.
Yeah, well, thank you, Osni, for having me.
And thank you all for joining. I'll see you tomorrow at 11.
All right.
Take care, Rebecca.